So in general, the theme is about randomness in computation. We all know it's useful in a variety of areas: cryptography, simulations of complex systems, and a lot of things. And one typical example is this of random sampling, where say you have 300 million voters in an election, and you want to quickly estimate what's going on. So what you can do is pick a random sample of a few people, say 400 people, with very high probability. If they're not lying, then you can actually get what's going to happen with pretty good accuracy. All right. So in general, randomized algorithms in a variety of situations outperform their deterministic, non-deterministic counterparts, or in some cases, you do not even know efficient deterministic algorithms. So one typical example is this of polynomial identity testing. So here you're given a polynomial p in some succinct representation, maybe an arithmetic circuit, or maybe a sum of product of linear terms.
This is in many variables.
Yes, it's in n variables, right? Yes, and you want to quickly estimate this. So a random strategy is just to evaluate it at a random point in a field.
You want to know what's identically zero.
Yes, identically zero. Yes, and there's this lemma, the Schwarzschild lemma, which says that multivariate polynomials of low degree have few roots, and this says that the random strategy works with high probability. But it's a major open question. So the naive deterministic thing would be to expand out the whole polynomial, check each coefficient of each monomial, which takes order n to the d time, if d is the degree of the polynomial. So that runs exponential in the degree.
What do you call a polynomial?
The polynomial it's an n-variate polynomial over a field f.
No, but how is it presented?
Yeah, right. So it's presented in a succinct way. For example, in computer science, there's this. So it's an arithmetic circuit, or for example, it can be presented as maybe a sum of product of linear terms. So
It's a formula.
it's a formula. Yeah. So yeah, it's a major open question if you can do it efficiently in n and d. All right. More generally, it's a major open question again in computer science if every efficient randomized algorithm has a deterministic counterpart, and BPP is this class of efficient randomized algorithms, and P is the class of problems which admit efficient deterministic algorithms, and whether they're equal. And you need to read this book. All right. And one area where you really need randomness is in cryptography, in encryption schemes, digital signatures, and many other applications which I'll not get into. But this is one area where you really need high quality randomness for your things to go through. So how do we get these random bits? Well, we could use really naive techniques, like maybe look at the keyboard strokes of users and see maybe the difference in times of his keyboard strokes and stuff. Or we could use more sophisticated techniques like look at radiations or atmospheric noise or electric noise. And there are some things called as true random number generators which sort of try to do these things. All right. And typically what is seen is that the stream of bits that's produced, it has some uncertainty or some entropy in it, but you do not get high quality randomness. That is, you do not get bits which are uniform and independent. And in applications, at least in cryptography and other areas, there's like actually papers which show that even basic cryptographic tasks you cannot do if you have correlated bits. Like there are attacks which completely break crypto systems. So many applications in computer science and other simulation kind of areas, you really need high quality randomness, that is stream of independent uniform bits. All right, so here's where this extractor comes in. So your extractor gets, say, n bits from some entropy source, and it's guaranteed that there's some entropy in it. That's all. It does not know what the source is. You want to apply this extractor. Say you know that your distribution or source has k bits of entropy. You want to apply this extractor and maybe output k over 2 bits, such that this distribution is very close to uniform. in statistical distance or variation distance. So you want uniform bits. And apart from this application, it has vast applications in computer science, so I'll not get into this. But it's a useful thing to construct.
When you're modeling the actual true independence, how long a sequence do you want it for? I mean,
right.
What kind of scale are we talking about?
In applications, in cryptography, you really are talking about maybe getting high quality random bits for. So each, you'd want to maybe mask your keys, say 1,000 bit long string.
1,000 bits. Okay.
And you want to do it repeatedly, so you need a lot of random bits. So now we want to model weak sources. So one initial model could be, look at a stream of independent bits where each bit is independent and it takes 1 with probability p, 0 with probability 1 minus p. But you do not know what p is, right? So from this stream, you want to output uniform bits. So this was in fact studied in the 50s by von Neumann, who give this very simple extractor. Well, you look at pairs of bits, and if they're different, you output the first bit. Right? So if it's 0, 1, you output 0. If it's 1, 0, you output 1, else you repeat. So if p is not too close to 1 or 0, then you'll succeed to produce uniform bits with very high probability. All right. Now the question is, how do you model a general weak source? This was thought of in the 80s, and the notion that's standard by now is mean entropy of a distribution. So we say a distribution X has mean entropy K if the maximum weight or probability it places on any element in its support is 2 power minus k. Right? So it does not take any element with too high probability. And in this talk, we'll talk about n, k sources. So these are distributions on n-bit strings, and it has mean entropy at least k. Right? So curly braces 0, 1 power n is the set of all n-bit strings, and your distribution X sits inside it.
Here again, the different bits they had, they're independent. You just
No. So a special case to think of is, you choose your favorite subset of 2 power k strings, and let your distribution be uniform on this subset. So it need not be a product set.
I did not understand the definition of mean entropy. So what is X? It's a long
It's n-bit.
N-bit string.
Distribution on n-bits.
and what is an element
A string, a sequence.
of which length?
N, yeah. So no particular, it's an arbitrary distribution on sequences of length n. And no sequence gets probability higher than
2 power
the
minus k.
minus k, then it's, for example, it's uniform on some arbitrary subset of 2 to the k element.
Exactly. Yeah.
It's an L infinity version of Shannon.
Right. So point-wise, you want does not assume with high probability. Right. Yeah. And a special case, as Avi mentioned, is where your distribution is uniform on some unknown subset of size 2 power k. All right. And a first definition you'd probably try to make of an extractor is it's a function. It's a deterministic procedure that does not know which n, k source you're using. It just knows that the distribution has entropy k, and maybe you want to output uniform bits. And for this talk, let's just try to generate one uniform bit. Well, but in general, you'd want to get almost all of the entropy out. So the key point is that your extractor cannot depend on the source that you're using. Right? So the extractor should work for any n, k source for sufficiently large k, say k to be log n or. But it turns out that there is some bad news here. It turns out that there cannot exist an extractor that works for any n, k source. In fact, it cannot work for any n, minus 1 source. So even if you look at the class of all distributions that has entropy at least n minus 1, you cannot even get one single bit out of it. Yeah, that's right. And it's a very simple proof, so I thought I'll show you. So assume you have such an extractor. So what this extractor does is it labels each n-bit string to either 0 or 1, right? So at least it labels one of these sets is like you either label at least 2 to the n minus 1 strings to zeros or ones, right? And now if you define your distribution to be on the larger set, then your extractor is essentially fixed on this distribution, right? So for example, if this is the larger part, so it has at least 2 power n minus 1 strings. And now if your distribution is over the set, then it has entropy at least n minus 1 because it's large set. But your extractor just outputs 0, right? So you cannot construct such an extractor. It just not exist. It's really bad news. And after this, there has been a lot of directions which was taken. This was noticed in the 1980s. And I'll talk about a particular direction where you say that instead of one source, now you have 2 entropy sources. So you have x and y, which are independent, and you're guaranteed that each of them have entropy at least k, min entropy at least k. And now your extractor gets a sample from x, a sample from y, and you want to output, again, you'd want to output maybe close to 2k uniform bits, but for this talk, let's try to output 1 bit. So more formally, you want a bit which is close to uniform, so you want that for any x and y which are independent and have entropy at least k, that the extractor outputs 1 with probability close to 1/2. Sorry?
And not identical distribution.
No, they're not identical. Yeah. Yes. So now the question is, does this exist? Well, it turns out that if you just pick a random function, then it's a good 2-source extractor for min entropy, which is pretty low. So you need both the sources to have min entropy at least log n plus order 1, and then a random function works. And if you go over probably all the functions, then it's going to take you really long time. So you want a polynomial time algorithm to generate uniform bits. So this question of explicitly constructing 2-source extractors was raised in the 80s again by Santa Vazirani and Shor Goldrick. Before going into explicit constructions, let's see what 2-source extractors imply in terms of combinatorics. So the matrix view is this, that suppose this is the truth table of yours. Suppose you have a good 2-source extractor that outputs 1 bit. Then you write out the truth table of the 2-source extractor, right? So this is the first input, this is the second input. So you have capital N rows, which is 2 to the small n rows, little n rows, and capital N columns. And each entry is just the output of the extractor. So now if your extractor works for min entropy little k, then it implies, so one thing it implies is that if you look at any capital K rows and capital K columns, and you look at these entries, then roughly half of them are going to be 0 and half of them are going to be 1, right? So it's a nice structure to have on these matrices. And in terms of graphs, it implies Ramsey graphs in the following way. Recall that a K Ramsey graph does not have any independent set or clique of size k. In the 20s, Ramsey showed that you cannot have a Ramsey graph with k, which is log n over 2, where n is the number of nodes. And almost matching this, in 1947, Edis showed that a random graph is a 2 log n Ramsey graph. So it's almost tight. And he asked, can you explicitly construct these graphs? Well, it turns out that if you have a good 2-source extractor, it implies the bipartite version of Ramsey graphs, which also implies Ramsey graphs. So what you do is, if you have a good 2-source extractor which takes 2 n-bit strings, so you have 2 to the n or capital N nodes on the left, capital N nodes on the right, and you add an edge only if the extractor outputs 1. Then again, if you look at, if it works for entropy little k and capital K is 2 to the k, you look at 2 to the k nodes on the left, 2 to the k nodes on the right, then you expect to see roughly half of the edges to be present and half of them to be missing, right? Because by the property of 2-source extractor that it outputs 1 with roughly half probability. Great. So what's known? Well, in the paper which asked to construct two source extractors, they showed an explicit construction for entropy n over 2. Recall that you can, existentially you know that you can do for entropy as small as log n plus order 1. After almost 20 years, Burgen, using really nice ideas from additive combinatorics, improved this to 0.499 n. Then in a work with my advisor David Zuckerman, we managed to get it down to polylog n, both the sources to log n power 75. Then almost immediately, Raghu-Meka improved it to log n power 10. Then in a series of works by Ben Arroyo, Tashma, and Dean Doron, and some work of mine with Shinley and Gil Cohen, we got it down to like log n times 2 power square root log n. And finally, the world record now is a work of Shinley, which gets it to log n times log n. So, well, I'll finish by giving some ideas how to get this log n out. Hopefully one of you will solve the open problems that I will. Before that, let's see what it means in terms of Ramsey graphs. Well, existentially, I just showed there exists Ramsey graphs for 2 log n, k being 2 log n, and a bunch of results give some explicit constructions which are exponentially off. And then from two source extractors, the Shinley's construction from recent implies explicit Ramsey graphs with log n times log n thing. So we are
Times or in the response?
sorry, log n to the log n power log
You
n.
want to get log n.
Yes, exactly. Yeah. So
This 2 to the root log n doesn't imply an extractor because it's not bipartite or something?
yes, it's a weaker object. It's a disperser kind of thing. Yeah. Right.
It's not because it's not bipartite, it's because it's empty graph versus non-empty graph in the Ramsey case. And
Whereas
in
it's
the
the
Python case, you really want it to be balanced.
I see. So
Up to
extractors
the
are actually
edge.
just stronger.
Yeah.
Yeah.
It's a density version of that.
Yeah.
Yeah. Right. And so some notes about how to probably go towards getting extractors for order log n entropy. So we know it for log n times log n. Turns out that with all the machinery that we have now, I'll present a relatively probably simple problem which one of you will solve, and just fitting this in the whole grand.
You have like 1 minute.
Oh, sure. Yeah. Then, okay. All right. So I'll get to the problem then. Well, you have two matrices, M and M prime, and M has, so think of each row as a random variable, x1 through xt, y1 through yt, and they're fat matrices, so they're, each row is of length 100t. And so each of these xi's, their marginal distribution, like each xi is uniform, right? And further, there is some row which you do not know which row it is. There is some row such that xi conditioned on yi is uniform, right? And now you're allowed to use an independent seed to output. So this function merger takes in this matrix M and the seed Y, and you'd want that the output contains some entropy conditioned on the merger's output on M prime and Y as well. Right, so all it's saying is that suppose you just had one row and it was independent, then you could just output that row, right? Now it's saying that somehow you want to merge this independence and output just one row maybe, so that there's some, ideally you'd want uniform, but given some machinery, it's enough to have just entropy. So this is related to some things which have been studied before in extractor literature. That's why I use this merger thing, like merging these rows. And so what is known is that we already know how to do it when, so the challenge is to do it with using a seed of length order t. So we know how to do this with length t times log t, which gives you the log n times log n thing. So
what's explicit here? The computation of merger or
so you want
whatever
a
function you
right.
see is polynomial time.
Yes.
And that's constructed how?
Right. So
I mean, you emphasize this as an explicit construct.
yes, yes. So yeah, you want to construct this function merger, which works in. So it can actually work in time exponential in t, because think of t as log n in the scheme of things. Yes. So the bottleneck here is to use order t amount of extra randomness to do it. So yeah, there are some ideas based on Kakai assets and stuff, which maybe I'll talk offline if someone is interested. All right.